Okay, so let's go ahead and get started. So today's class, the big topic is FSM, which stands for finite state machine. This is really what the class has been working towards, because what you'll see is that the finite state machine is made up of both sequential circuitry and combinational circuitry. So, last week we first started talking about sequential circuits that have memory, and then all the weeks before that we were doing topics involving combinational circuitry that doesn't have memory. Okay? So you'll see that an FSM contains both, both sequential that has memory and also combinational. Now, there's a few things I want to talk about before we get to the FSM. One is a clock divider, and on each table I put code that models the clock divider, and we'll go through that example. And then I just want to talk briefly about a counter. And then, like I said, the majority of class is going to be on an FSM. We'll probably take a break because the previous two sections, all that I got to talk about, this example along with the code to model an FSM, it will take a while. In both sections earlier today, we took a break about halfway through, but it still took about 90 minutes or so. So be prepared. Also, I just want to mention, I haven't finished grading the midterms. I got about halfway done this weekend, and I know I'm not going to have enough time to finish tomorrow, so I need another weekend to finish them. So I will have them, or I'll have your scores a week from today. Tuesday and Tuesday should have them, because like I said, I just need another weekend to get through. All right, but where we're going to start is with what's called a clock divider. And what this module does is it takes a frequency and cuts it down to a smaller frequency. So you can see here that the clock divider has input CLK, and at the input is 100 megahertz. The reason why I chose 100 megahertz is because, as I mentioned last week, the basis 3 board that you have, it operates at 100 megahertz. And then the output of our clock divider, this S clock, S just stands for slow, like slow clock. So, we're taking this fast clock of 100 megahertz and we're going to cut it down to a smaller frequency. Now, also, we talked about this last week, that the time it takes for a waveform to repeat, call that the period, that we label capital T. And then what's the relationship between period and frequency again? Yeah, so period is 1 over frequency, or frequency is 1 over period. And we talked about, or we calculated, or at least somebody punched into their calculator, what the period of 100 megahertz signal is. You remember what that period is? It's the reason why in the sim files that you've been creating, you put number sign 10, test case, number sign 10, test case, number sign 10, test case. You remember what the number sign 10 represents? 10 nanoseconds, exactly. Yeah. And that's the period of 100 megahertz, because again, that's the basis board is operating at. So when you put that number 10, test case, number 10, test case, you're separating the test cases by one cycle, one cycle of this 100 megahertz clock signal. So yeah, 10 nanoseconds. And then what's nano? 10 to the what? Minus 10 nanoseconds to 10 times 10 to the minus 10. Okay, you'll see why we need that coming up shortly. So now, if you look at the code, and again, each table should have this handout here that has the code for the clock divider. I put one hand up. I was hoping that people at the table would take a picture of it and look on their phones at it, or you could gather around and all look at the same handout if you want. Okay, but you should be looking at that as we talk about this. So if you look at the very top of the code, you'll see this. You'll see number sign, and then in parentheses, you'll see parameter max count equal to 1. Well, what this code is doing is it's essentially making this max count a variable. And then it's assigning it to a default value of 1. And using this parameter feature in system Verilog, it's also in Verilog. It's not something you have to do, like it's not a requirement or anything. But a lot of times it can be handy because once you define a parameter like this, you can easily change the value. So even though this is the default value, if I wanted to change this, I can do that in the structural design, right? To say this clock divider, is part of a much larger design. And in that structural file where you make the connections, at the beginning of the line for this clock divider, right before you hit the parentheses where you start to do the connections, if you want to change this default value, all you have to do is put number sign and then the new value, right? So if we wanted to change the default to this 50 million in the structural design, I could just put number sign 50 million before I start making the connections for this clock divider. So that's especially useful when you have like multiple modules that have different, where you need different, variable values. Like, say you had like 4 clock dividers in your same, the same design, the same overall design. Well, I could use the default value for one of those for the max count. And then for the other 3, if I wanted different max count values, I don't have to generate 4 different design files. I can use the same design file, but just make the change in the structural file. Again, on the line where you make the connection. So having a parameter like this, in some cases it can be advantageous. It can, save you some work. But again, it's not something that's required. Now, also in that code that you have on that handout, can you tell me how many bits count is declared as? 30, right? 29 to 0. So, 0 is our least significant bit number. 29 is our most significant bit number. So yeah, count is 30 bits. So what range of values do we have with 30 bits? Like we can go from what number to what number if we have 30 bits. And this value that we use for max count is an unsigned, right? We don't have any, we don't want any negative values for max count. So if you have an unsigned number that's 30 bits, what's your range of values? What to what? The first one should be easy because what's the minimum if you don't have negative values? 0. Yeah, 0. Okay, but what would be the high number if you have 30 bits? Or how would you figure it out? 2 to the 30 minus 1, 30. Sometimes people just say 2 to the 30, but it's 2 to the 30 minus 1. See, the way I remember is I just think of smaller bits. I know if I have 4 bits, we have values 0 to what? You have 4 bits, you can represent values 0 to. What's the highest number you can represent with 4 bits? Yeah, 15, right? You can't represent 16 with 4 bits. You need 5 bits for 16. So if I have 4 bits, 0 to 15, and 15 would be equal to 2 to the 4 minus 1. Right? So, if you know how to get the range for a smaller number of bits, you know how to get it for a larger number of bits because it's the same relationship. Okay. Now, if you were to actually figure out 2 to the 30 minus 1, you would get, because I figured it out earlier. Now, where did I do? What's that? It's big. Because it's 1 billion 73 million 741,820. Because 2 to the 30 is 1,073,741,824. So subtract 1, 8.2. Okay. Now this brings up something else that's not really required for this class, but it's something that will be talked about in CPE133 either on the first or second day, and that's in base 2. 1K does not equal 1,000 even. Like when we say 1K in the digital world, right, the base 2 world, 1K doesn't mean 1,000 even like it does in base 10. Does anyone know what 1K in the digital world equals? 1,096. Not 1,096. Say that again? Yeah, it's 1,022. Does anyone know why it's 1,024 and not 1,000 something else or some other number? It's 1,024 because 2 to the 10, right? 2 to the 10 is the whole number power of 2 that's closest to 1,000. You take 2 to the 10, you'll see it comes out to 1,024. Okay, so 64K is base 2. This is base 2 over here. Not equal to 1,000. But 64K in base 2, it's not 64,000 even like it is in base 10. It would be 64 times 1,024, which equals 65,536. So if you go work someplace and they want to pay a salary of 64K, ask for it in a base 2 sense. Say, can I have that in the digital sense? I can pick up another $1,536, right? I actually tried that at my credit union one time, and they just looked at me cross-eyed. They don't understand base 2 at the credit union I go to, so it didn't quite work there. But anyway, now also in base 2, 1 meg is not equal to 1 million even like it is in base 10. 1 meg in the digital world is 2 to the 20. Right? If you figure out 2 to the 20, it's like 1,048,000 something. So like you ever win the lottery, ask for it in the binary sense, right? You pick up another 48,000. And then there's 1 gig, okay, which isn't equal to 1 billion. It is in base 10. 1 gig would be 2 to the 30. So this is 1 gig right here in the digital world. Okay, so like I said, this here really isn't important for what we do in this class because we don't deal with numbers that big typically. But in CPE133, this is usually talked about at the very beginning of the course. I'm giving a little preview of some of the things that we're talking about in that class. Okay, another thing though that's part of that code that you have on the handout is what count is initialized to. Now count is declared as 30 bits, like we said before, and then see after it's declared as 30 bits, see that equal to 0. That's just initializing count to 0. Okay, so the next thing we're going to do is we're going to step through this code and see how this code is producing lower frequency square wave at the output than what we have as the input. And for this example, we're going to use a max count of 50 million. Okay, so we're changing this default to 50 million. Okay, so now if you look at this code, there's an always FF block, which we talked about. And you can see that it's sensitive to the positive edge, the 0 to 1 transition of the clock. So if every 0 to 1 transition of the clock, and this is our clock signal right here, okay, our 100 megahertz square wave. So in every rising edge, this is our 100 megahertz down here. See what's up there? So on every 0 to 1 transition of the clock, this always FF block is going to be evaluated. And you can see, within the beginning and the end of the always FF, the first thing is count is incremented by 1, right? We initialize this to 0. So on this first clock edge, count's going to go to 1. Then in the if, you can see count is compared to max count. And if it's equal, then the if is evaluated. If not, count just gets incremented again, right? So count is going to keep incrementing until it gets up to 50 million. And our S clock Oh, I forgot to mention, also, up at the top, S clock is initialized to 0. If you look at the top here. So our S clock starts at 0, and it's just gonna stay 0 for 50 million clock pulses, right? Because it's not until that 50 million clock pulse that now count equals max count. And when count equals max count, the if is evaluated. First thing that happens is count is initialized back to 0, and then S clock is inverted, right? Remember the little tilde means inverted? So S clock will stay low for 50 million clock pulses, right? 50 million of these 0 to 1 transitions, and each clock pulse is 10 nanoseconds. So if you want to figure out the time that this S clock stays low to begin with, well, you just take our max count of 50 million and multiply that time, the time of one cycle, right, which is our 10 nanoseconds. So 50 times 10 to the 6, right, mega, times 10 to the 10 minus 9 nano. What is that going to give us here? How much time is that? It's 500. Yeah, what do we call 10 to the minus 3? Really? So this is 500 milliseconds. And how many seconds is 500 milliseconds? Half a second. So you see, S clock is going to stay 0. That's what it starts at. And it stays 0 for 50 million clock cycles, period. Then it gets inverted. So it's going to get inverted to 1. And then it's going to stay 1 for 50 million clock cycles. So it will stay a 1 for half a second. Then it goes back to 0, and it just keeps repeating. So what this code is doing is it's taking this 100 megahertz fast signal, right, fast frequency, and it's making it into a very slow frequency, right? If you have a square wave that's low for half a second and then high for half a second, what's the period? 1 second. And what's the frequency of a signal with a period of 1 second? 1 hertz. So you see, this would be dividing that clock frequency by 100 million, right? Because it's taking 100 million hertz and converting it down to 1 hertz if our max counts 50 million. Okay, so the reason I go through this example is a couple of reasons. One, there's a clock divider in lab 6. Okay, now lab 6 isn't due until next week. Okay, Friday of next week. Due this Friday is lab 5. Okay, but when you get to lab 6, you'll see that there's a clock divider. So it's something we give to you. But when we get to talking about lab 6 on Thursday of this week, I'll point out that in the clock divider for lab 6, you're going to have to change an integer. And that integer that you're changing is the same as what this max count is doing. Okay, by changing that integer, you're changing the amount of time that this output square wave stays low and goes high. So you're affecting the frequency of this slow clock by changing that integer. Okay, and this example shows going from 100 megahertz to 1 hertz, but you can go from any frequency to any other frequency just by picking the right number. And again, the way you pick that number is just by doing an analysis like this, right? You just got to kind of work backwards. You got to say, okay, what kind of period do I want here? How many cycles is that going to be? What's the frequency of this? Because that gives me the period times the number of cycles, and then you get responsible. Okay, so that's one reason, because lab 6 has a clock divider. Another reason why it's good to know about this is depending on what you pick for your final project team, a lot of times, depending what you pick, sometimes you don't need it, but a lot of times you do need some sort of clock divider, and this is what you could do. Okay, you essentially take this code and modify it to what you need to do. Okay, so any questions about the clock divider? All right, the next thing, and I don't want to spend a whole lot of time on this. I just want to point out how a counter relates to a register. Okay, because we talked about registers the end of last class, right? That a register is just made up of a collection of flip-flops, right? If you just have a single flip-flop, it can store a single bit. But if you want to store multiple bits, well, you need multiple flip-flops, right? You need a flip-flop per bit that you want to store. Well, a counter is just a slight extension from a register. I call a counter register plus because it does the same thing a register does, plus it will increment the output by a certain amount. And as an example of a counter, there's this one in CPE133. And again, on every table, I put this diagram that you've seen a few times before, which is the microprocessor that you build in CPE133. And if you look at this diagram, you'll see in the lower left-hand corner, this module PC. PC stands for program counter. Now, when you take that class, you'll learn the purpose of it. But the main thing I wanted to tell you about at this point is that when you model this program counter in CP233, it's going to be the same code that you use to model the register in this class, plus just this added one thing. See this little box with the +4 that's connected between the output of the counter and the input? Well, that's going to increment this output by 4 every time that this input that's labeled PC_WR is activated during the time of a 0 to 1 transition of the clock. Okay, because this input, and WR, by the way, stands for write. And you'll learn about what read and write means in that class if you don't already know. But when this write, which is the same as an enter, when this is active during the 0 to 1 transition of the clock, this input will now be in the register and accessible at this output. So every time that this write is active at the time of a 0 to 1 transition of the clock, the output of this counter will increment by 4. Okay, so let's say you start out by resetting it. This RST just stands for reset. And remember, we talked about, just like with the register, when reset is active, and again, this is a synchronous reset, so not only does it have to be active, but you gotta have the 0 to 1 transition of the clock. Well, when you have those two things, the output's gonna go to 0. So typically, you'll start by resetting this counter to 0, and then after that, you're just incrementing it by 4 on every clock pulse that this write input is active. Now, you'll learn why this is 4 when you take that class. I mean, there's a very important reason why this is 4. This can't be 2, can't be 3, can't be any other number other than 4 for your microprocessor to work correctly. And again, when you take the class, you'll be given the reason why. Okay, but the main reason, again, I bring this up is, one, as an example of a counter, but 2, just to show how close counters are to registers, something you already know, right? Because again, a counter is just a register with an amount that it increments. Okay, so when you model a counter in Verilog, one way to do it is you have the same code as what you do for a register. Okay, so I would hang on to your register code in this class when you take CP233, because you can use it here in CP233. And then you would just need an additional assign statement, okay, to take care of this +4. That you would just assign whatever you call this internal signal on this side of the +4, like I called it T2. You would just assign T2 to whatever you call this side +4. So here it would just be T2 +4. All right, and then you're going to let the software handle this addition as opposed to making some sort of RCA. The only time you make an RCA is in this class, because again, it's a good example of a first structural type of design. But after that, any type of addition, you're just going to use the plus, and then Vivado, the power of Vivado will, model the circuitry you need. And the part of the circuitry that you'll need for this +4 will be some sort of adding circuit. Okay, you'll also learn in CP212, I don't know if it's 233, it might be later, but you'll learn eventually that there's much more efficient counters than RCAs. Like, they don't use RCAs because they're very inefficient. There's better ways to do counting. Okay, so any questions up to this point? Because we haven't talked about FSMs yet. That's the next thing. Okay, we're going to do the basics of FSMs. Then I'm going to do an example using what's called a state diagram, and then I'm going to show you the Verilog code and model in FSM. Okay, so you ready for FSMs? All right, let's talk about FSM. So here's the block diagram of an FSM, and notice that I've got most of it in black, but there's a couple of things here in blue. Okay, and that was on purpose. Okay, because there's two types of FSMs. Okay, there's what's called a Moore and a Mealy. And before anyone asks, it's usually people ask at some point, as far as I know, there's no relation to Dr. Mealy. This is a totally different Mealy. Okay. And I'll explain the differences between these two in just a second. But as far as the diagram goes, just what's in black is a Moore FSM. And if you have what's in black along with what's in blue, that's a Mealy. Okay, so a Moore would not have these blue lines. It would just be what you see in black. A Mealy would have what's in black and also what's in blue. Okay. Okay, so notice that an FSM, whether it's a Mealy or a Moore, it has a next state decoder, has an output decoder, and it has state registers. Which of these blocks is sequential? There's only one block. Which one is it that's sequential? Should know this. If we have sequential, it has what? Memory. It has memory. It has what kind of input? Clock. So right away, see, this is a giveaway. If you have a block, a module that's got a clock input, it's sequential. It has memory. So you see, this is sequential. And then these other two blocks are decoders. They're combinational. I'm just going to write combo for combinational. Right? A dead giveaway when you have a combinational is you don't have a clock. There's no clock input to those modules. So you see, this is why we couldn't talk about FSMs until now in the quarter, right? Because it wasn't until last week that we ever said anything about sequential, right? For the first time. So, before you can talk about an FSM, you have to have some understanding of combinational and sequential, because an FSM contains both. Okay. All right, well, these state registers, having memory, they contain, what state we're at. So where we're at, where we are at. Okay, and the next state decoder, that's circuitry that's going to determine where we're going to go next. Okay, so the next state decoder is where we go next. Okay, and then this output decoder, it determines the output. And this is where the two different types, the Moore and Mealy, differs with the output decoder. Because if you have a Moore, output only depends on the state you're in. Okay, so a Moore output only depends on the state. A Mealy output depends on the state and external inputs. Okay, and you can see this in the diagram, right? Because if you just look what's in black, right? If you just ignore what's in blue, the only thing that's feeding into the output decoder when it's a Moore are outputs coming from the state register, right? Which is the state we're in. If it's a Mealy, well, then you do include the blue, and the output now depends on not only the state we're in, but also these external inputs. Okay, so that's the difference between the two. It's what's happening here at the output decoder, right? The more only depends on the state register output. The mealy depends on the state along with external inputs. So Dr. Benson, she has this saying to help remember the difference between mealy and more. I think it's a good one because it's short, concise, and I think very descriptive. And that's, she always says more has less. Right, but the more only depends on the state, right? Where the mealy depends on the state and external input. So I think that's a good way to remember. More has less. I think that's a good way to remember. I think it's a good way to. Okay, so any questions up to this point? Actually, we're doing good on time. My other sections, I think we were closer to the top of the hour. So I took a break in my other sections at this point because we're going to start a state diagram and then go into the code, and that's probably going to take over a half hour. Do you want me to keep going, or you rather take an early break? Keep going? Okay, we'll keep going. All right, so now we're going to turn the camera on first. So my streak is still alive. Okay. So now we're going to get more specific, okay? This was kind of like general information about an FSM. Now we're going to get more specific. And I'm going to use this example, a finite state machine counter. And, you know, I want to preface this with that there's no special reason why I chose an FSM counter. It's just I had to choose something for an example, and that's what I decided. You know, you can make just about anything out of an FSM. It doesn't have to be a counter. It can be all kinds of stuff. In fact, your CPE133 microprocessor, if you look in the upper right-hand corner, CU FSM, that's control unit FSM. And if you look at these outputs of the FSM, they're either write or read outputs. And you'll learn in CPE133 that writes and reads, you know, write is like an enter, putting data in, and a read is getting data out. Well, these are all time critical, you know, outputs. Okay, they're controlling the reads and the writes of all these other modules, and you know, they're very time critical. So, you know, FSMs can be used to, you know, control, you know, other modules through read and writes, and you know, like I said, you can just about make anything out of an FSM. But no matter what FSM you're creating, you always start with the state diagram. Okay, this is probably one of the most important topics of the quarter here, state diagram. And the first thing in a state diagram is to have a legend. Okay, and you know what I'm going to show in my state diagram and also use for my legend is what typically is used. Okay, but you know, there's different ways to, you know, represent state diagrams. It's, you know, it can be very personalized. I don't think there's like one standard way of doing it, but what I'm about to show you is, you know, what we use here at Cal Poly, at least most instructors. And that's, there's a circle. That circle represents a state. Okay, then inside the circle, usually you'll see like a line like this. Above the line is the state name. And you know, you can name the state whatever you want, right? So you can put anything to the name. But then the next thing is inside the circle. Okay, inside the circle, we write more outputs. It can be output singular, or it could be more than one. And you see, if you think about it, it makes sense that pictorially we would want to put the more output within the circle that represents a state, because that's the only thing a more output depends on, right? More output only depends on the state which the circle represents, right? So it sort of makes sense that pictorially you would put the more output within the circle. So here, what I'm going to do is for each one of these numbers in our sequence, because see this counter that we're going to build an FSM for, its sequence is 2, 0, 7, 5, 3, and then it just keeps repeating. Okay, so this counter is just going to count these numbers in this order just over and over again. And I'm going to represent these numbers as binary numbers, or binary bits, I should say. So what's the minimum number of bits to represent these numbers? How many fingers you got? I can't see without my glasses. You say 4. Well, we could use 4, but that's not the minimum. 3 would be the minimum, right? Because I only need 3 to represent 7, right? 1, 1, 1. Yeah, so I'm going to label it B2, B1, B0, right? It's three binary bits. Now, you don't have to represent your more output as binary. I mean, you could also represent it as a base 10 if you wanted to. Okay, but I just decided, because I wanted to ask you that question about minimum bits, to do it as bits. That's the only reason. Okay, so we got our circle that represents the state. We got our more output that goes within the circle. Another thing that you need in your legend is this here. See, it's this curved arrow. The curved arrow represents a clock transition. Okay, so it's either a 0 to 1 transition or a 1 to 0 transition, depending on whether you have a rising edge triggered FSM or a falling edge triggered FSM. See, it should make sense to you that you could have either of those, right? Rising edge or falling edge for the FSM, because it contains sequential circuitry, which depends on the clock. Right? So just like you can have rising edge triggered flip-flop, rising edge triggered, right, register, right? You can have rising edge triggered or falling edge triggered FSM. All right, so this is the legend we're going to start with, and this is probably the most basic you could have. But we're going to start with this, and then we'll make some modifications to it coming up shortly. But starting with this legend, I would now do my state diagram. And the state diagram is going to show the states in order to do this sequence. Okay, so I have 5 numbers, right? 5 more outputs, so I'm going to need 5 circles, 5 states. And it doesn't matter how you orient the circles. I'm putting them, as you see here, in a circle, but you could put these all in a straight line or vertical. It doesn't matter how you orient the circles that represent the states. Okay, and then I'm going to name my states like this. I'm going to call this state A, so STA, STB, STC, STD, and STD. But again, you can call them whatever you want. Now, for each of the states, I'm going to put the more output. Okay, these numbers here are going to be more outputs where they only depend on the state. So when I'm in state A, we have a 2, right? So I put 2 in binary. When we're in state B, we got a 0. State C, all 1s. State D, 1, 0, 1. And state E, 0, 1, 1. Okay, and now I'm going to put in the clock transitions that shows the order of the sequence. So if we're starting here at state A, well, we then go to state B. And then from state B, we go to state C. And then from state C to state D. And then state D to state E. And then since we repeat, when we're in state E, we just go back to state A. Now, another thing that's important is that if you don't have anything written next to this curved arrow that represents the clock transition, okay, so when nothing written by curved arrow, that's representing what we call an unconditional clock transition. Okay, what we mean by that is that all it takes to go from one state to the other is a clock edge. So, once we're in state A, once we get a 0 to 1 clock transition, we're going to go to state B. And then on the next 0 to 1 clock transition, we're going to go to state C, and so on. Okay, so if you don't see anything written next to these arrows, that just means unconditional, that once we get a clock edge, you're going to get that transition from one state to the other. Okay, now we're going to add some things to our state diagram here, and I'll show you, an example of a conditional transition, but this is what you would have for unconditional. Okay, so do you have any questions up to this point? Like I said, this is probably the most basic state diagram you could ever have, but now we're going to add some things to, make it a little bit more interesting. But any questions up to this point?
Something written by the curved arrow is like that first.
Yeah, I'm saying that if you don't have anything written by the curved arrow in your legend, that means that we have unconditional transitions, that whenever there's a clock edge, we're going to transition from one state to the next. Yeah, you're going to see an example of unconditional or conditional coming up now. Okay, ready? Okay, so let's add some things to the state diagram and therefore add some things to the legend. One thing we're going to add is a reset. So if you want to add a reset, you just add an arrow like this pointing into the state. And I'm going to make this an active low reset. Okay, so remember, just like in a timing diagram or, on a symbol for a component like a flip-flop, the bar means active low. Okay, so this is active low reset. And then also, and there's no real way to show this pictorially, so you would just have to make a note. We're going to make this asynchronous. Okay, we're going to make this active low reset asynchronous. So you just have to write that it's asynchronous or synchronous. Now, let me just put a disclaimer at this point. And the disclaimer is that when you take CPE133, you're going to learn in that class that resets, especially resets in a microprocessor, they're always synchronous. When you have any sort of, complex type of logic circuitry where there's many modules and each module has a reset, well, you want to reset everything at the same time, as close to the same time as you can. And that's more likely to happen with a synchronous reset than an asynchronous. Okay, because synchronous all happens on the same clock edge, where asynchronous could be, happening at slightly different times. Okay, so I just put that out there because the only reason I'm making this asynchronous in this example is because you haven't seen an example of an asynchronous input in Verilog yet. So I wanted to make this async because when we get to the Verilog code, I'm going to show you, how you make something async. Okay. So, when you take CPE133 and the professor says, hey, all these resets are synchronous and resets are always synchronous, don't go, oh, well, Perk said it was asynchronous because we did an example. Well, I'm only doing this example for academic reasons. Okay, so I don't want CPE133 professors yelling at me, okay? All right, now the next thing we're going to add is we're going to make this clock transition conditional instead of unconditional. And we're going to make it conditional based on an input enable. Okay, and enable. And, I've decided that when enable is active, we'll go from one state to the next. If enable is not active, we're just going to stay in the same state. Okay. The other thing that I decided as the creator of this example is that when this async reset is low active, we're going to go to state A. Okay, so in the state diagram, to show that when reset is active, goes to state A, you would just draw it like this. Okay, and now, when our enable is active, we would just progress to the next state. So if it's active enable, we'll go from state A to state B. And if we're in state B and enable is active, we'll go to state C. If we're in state C and enable is active, we go to state D, and so on. If enable is not active, we're just gonna stay in the same state. So, if we're in state A and enable is not active, we just stay in state A. So I would show it like this, right? When enable is not active, when it's low, we stay in A. When we're in state B, if enable is not active, we'll stay in that state. And same thing for all these states. It's only when enable is a 1, is an active high, that will progress through the sequence. Okay, so I think I got them all here. Okay, so everybody see what we're doing, right? So you see now the clock transition is conditional, because depending on the value of enable, that's going to determine whether we go to the next state or whether we just stay in the same state. As opposed to unconditional, where we just go to the next state on every clock edge. Right? So everybody good?
Does it matter what way you get it?
Oh, like if I had it this way instead of that way, yeah, it doesn't matter. Yep. All right, we're gonna add another thing. And the next thing we're gonna add is a mealy output. Okay, a mealy output, like we said earlier, not only depends on the state, but also depends on external inputs, which in this case is our enable. So in the state diagram, if you have a mealy output, it doesn't go in the circle, right? Because that's where more outputs go, which only depend on the state. Mealy outputs go underneath any inputs you have here. We put a slash, and our mealy output is going to be an LED. Right, so you see this LED, that's a mealy output. Okay, so more outputs go within the circle, mealy outputs go outside the circle. Okay, and then again, as the designer of this example, I decided that I want the LED to be on when we start the sequence, and I want the LED to be on when we get to the end of the sequence. Within the middle of the sequence, or if we're not progressing through the sequence, I want the LED to be off. So the way I would show that in the state diagram is here's where the sequence starts, right? Because 2 is the first number, so if we progress to the next number, we've started the sequence. So you see, I want the LED on for that, so I would represent it that way. Also, I want the LED on when we go from the last number back to the first number. Okay, so I put slash LED there. All the other times, if we stay in a state or if we're anywhere in this part of the sequence, I want the LED to be off. So I would put LED with a bar over it there, LED with a bar over there. Everywhere else, we put an LED with a bar, meaning the LED is off. And if I miss one, let me know. Try to get all of them here. Did I get all of them? I think I got all of them, right? Because we want them all off here. It's only at the very beginning and the very end we want it on. Okay, and again, I just made that up. Okay. But now you've seen just about everything in a state diagram: more output, mealy output, unconditional, conditional, transition, reset. Now you'll see in the activity, because the activity that you have for today is basically what I'm showing you in reverse. Okay, like I started with the state diagram, and then from the state diagram, I'm going to show you the Verilog code that represents that state diagram. And if it represents the state diagram, it represents this sequence. Okay, and it's going to model the FSM to give you this counter. The activity that you'll do, it's the opposite. We give you the code, and then from the code, you got to write the diagram. And in the activity, instead of just one input, there's 2 inputs. So it's not that you always just have one input. Sometimes there's more than one external input. Also, sometimes you have more than one more output. This one only had one more output, but sometimes you have multiple more outputs. Sometimes you have multiple mealy outputs. Okay. You'll see next week when I give you information about a 4-bit multiplier, which is your individual final project. You'll see the state diagram for that 4-bit multiplier. It actually has an output that is a more output for part of the state diagram, and it's a mealy output for another part of the state diagram. Okay, so there can be all kinds of various variations of this. Okay, but it all kind of comes back to these basics. Okay, so are you ready for the Verilog code that's going to model an FSM? See, the good news is that once you have a state diagram for whatever you're creating your FSM for, to write the Verilog code from this state diagram, it's really cookbook. You know, usually the toughest part of creating an FSM is coming up with the state diagram. Okay, this state diagram, you know, for this example, because it's the first one you've seen, you know, I made it, you know, as straightforward as I could. But lab 6 that you'll be able to start on after Thursday's lecture, and I'll talk about lab 6 on Thursday. You'll see the state diagram for lab 6 is a little bit more challenging than this. Okay, and you know, you can get state diagrams that are pretty, you know, pretty challenging. Now, good news, in CP233, the state diagram for that FSM, the control unit FSM, it's actually pretty simple. I would say it's almost as simple as this. It's not very complicated. But what makes that FSM in CP233 challenging is part of the code that I'll get to once we talk about this. But before I start talking about this, are we all set up to here? State diagram. This is making sense. All right. So now let's get to the Verilog, and this is where I got to refer to my notes so I don't make any syntax errors or try to minimize them anyway. Okay, so this is the system Verilog code that you would need to model an FSM. So like any module, you know, you got to give it a name. I called it FSM counter. And then you would declare your inputs and outputs. And that's actually something we can do that we forgot to do, or I forgot to do here. Let's come up with the high-level black box diagram for this FSM counter. So all you have to do to come up with the inputs and outputs for this FSM is to look at your state diagram, right? Because what inputs do we have here? Looking at this state diagram, what are inputs here? Is reset an input? Is what's inside the circle? No, that's an output. Is LED an input? No, that's an output. How about enable? That's an input. So reset and enable are both inputs. What other input is there? What other input is there? Because you always have this input when you have something sequential. And remember, an FSM has a sequential part. Yeah, the clock. You always have a clock. So those are our inputs. You have clock, reset, and enable. And what are our outputs? LED and count. Right, we'll call the count the sequence, or you call it sequence, I guess. I call it an LED. And how many bits is our count output? How many bits? Look at the state diagram. 3. All right, so you see that would be the high-level black box diagram for this FSM. All you got to do is look at your state diagram. You can get the inputs and outputs. Okay, so now we're ready for the code. So again, you declare your inputs and outputs, and then after that, this is something you haven't seen before. Okay, you need these 2 lines for an FSM, okay, in Verilog or system Verilog. So you type this here, type def, which is short for definition type. And then enum, okay, E-N-U-M, that's short for enumeration. And then within braces, you put the names of your states. So you see, within the braces, you put state A, state B, state C, state D, state E. You know, I didn't have enough room here, so that's why I just put the dots here, but you would have to name all your states that you have. And then after the braces, you put states here. So this is declaring those names as the states in your FSM. And then you also have to declare states NS and PS, where PS stands for present state. Okay, so that's the state we're in. And NS stands for next state. That's the state we're going to next. Okay, so you have this, and now after you declare your states, and by the way, when we look at the activity that you're going to do, I'll point out that in the activity, these two lines are different. Okay, there's actually a different way to declare your states, but I highly recommend doing it this way. Okay, doing it this way has some advantage that I'll talk about when I show you the other way of doing it. Okay, but the next thing now that comes in your code is something you've seen before. It's an always FF block. So you put always underscore FF, at symbol, and then in parentheses, pause, edge clock. Okay, because we're going to make our FSM, we're going to make them rising edge. And then, and this is something you haven't seen before, because everything you've seen before with the always FF, it just had pause, edge clock within the parentheses. But here I'm going to add, you know, comma, and then I'm going to add neg edge reset. And I'll explain what the neg edge reset is doing in just a second. And there's no semicolon here, so just parentheses. Okay, then we have a begin. Okay, and then we're going to use an if. Because if reset is active. Okay, so if reset is active, and this is active low, so that's why I put the exclamation point here. Well, then present state, we're going to assign, and remember, since it's within an always FF, you have to use the arrow, not just the equal. Okay, remember, in an always comb, you just use the equal, and an always FF, you use the arrow. So if reset is active, looking at our state diagram, right? If it's active, meaning it's low, we're going to state A. So we're going to assign present state to state A. Else, okay, if we're not resetting, well, then we're going to assign present state to next state. And next state is going to be determined by combinational circuitry. So the next state is going to be determined by another block that's an always comb block. Okay, does that make sense? Right? So getting back to this, we need an end for this begin. So let's see, where am I here? Yeah, so right, this end goes with this begin. So here's your always FF. And you know, it shouldn't be a surprise that this code for the FSM is going to contain an always FF and an always comb, because an FSM is made up of sequential and combinational. So it sort of makes sense that you would model it with both types of blocks. And this block is modeling the registers. It's modeling this state register block. And, you know, whether you're doing, you know, this sequential counter, or whether you're doing lab 6, okay, which is going to be a sequence detector, again, I'll talk about on Thursday, or whether you're doing the FSM that's in CPE133, or you're doing an FSM for your final project, because that's one of the requirements in your final project, your always FF is going to be just like this. You know, if you have a reset, that goes first, and if you're not resetting, well, then you're just setting present state the next state. So always FF is always this simple for an FSM. Okay, usually where people get into trouble when they go to do this is they often overcomplicate always FF. Like they try to add stuff in here that should really be an always comb. Okay, the other thing that comes up, and I'm guilty of this a lot, is making sure you have ends that match the begins. You know, you got to have an end for every begin that you have. Sometimes it's easy especially when we get to the always cone blocks, you miss one of those. Okay, so that's your always FF. After that comes your always cone block. Okay, so you're gonna have an always underscore cone. We'll need a begin. Okay, now the first thing I do in the always cone block is I'll initialize my outputs. This is something that you don't have to do, but by doing it, you eliminate, some code that you would have to write if you didn't do this. So I think it's a good idea right after the always cone begin to set your outputs to an initial value. Okay, so I'm going to set count to 0. And since it's 3 bits, it's 3 zeros. And then also I'm going to set LED to 0. Okay, that's only 1 bit. Okay, so again, this line is just initializing our outputs. Okay. Okay, then after you initialize your outputs, now comes a case statement. And remember, in the parentheses of the case, that's what's called the sensitivity list. So whatever you put in here, that's when the case is going to be evaluated. And we want the case to be evaluated every time present state changes, right? Because when present state changes, this block is going to figure out where we're going, what the next state is. Okay, so inside the parentheses, this is going to be present state. And sometimes people make a mistake and they put next state here, but you want present state because that's what gets updated. Okay. All right, and then inside this case, we're going to have an if statement. Actually, did I forget something? Oh, I forgot something. Sorry, let's back up 1 minute. My mistake here. Or no, wait, I just forgot. Let's see, this is right. And then before we do the if statement, that's what I messed up. Once you write this case and it's sensitive to present state, the next thing comes your different options of the case, which are going to be your states. So, in this case, we're going to have option state A, and we're going to put what's happening in state A here. Then we're going to have state B, then state C, then state D, then state E. And then what do you always end your case statement with? If you have your options, and then there's something that you always have to end the case statement with, otherwise it's going to generate a latch. Default, yeah. So, we'll have state A, state B, state C, state D, state E, and then we got to have a default. Now, I'll do a couple of these states here in class, and then I think after we do a couple, I think you'll get the idea, because it's pretty repetitive after you've done it, okay? All right, but state A. So state A, and then we need a begin, another begin here. So this is the begin for the always cone, and then this is the begin for state A. And now, the very first thing to list for each of the states, once you're writing for a state, is what the more output equals, right? Because the only thing that determines a more output is the state you're in, right? So when we're in state A, this more output, the count, is equal to a binary 2. So you see, that's what I'm going to put. Let's see, where is it? Right after this begin, I put count, and then equal 3, tick mark B, 0, 1, 0, semicolon. See, this is the more output. All right, then after the more output, now you're going to use an if statement to determine, based on enable, how we're going to progress from state A. If enables 1, we're going to go to state B. And also we're going to turn the LED on, which is a mealy output. If we're in state A and it enables 0, well, then we're just going to stay in the same state and we're going to turn off the LED. Okay, so the way that would look like in the code is that you would have an if statement. So if enable, okay, we need a begin, okay, because we're going to have 2 things here in our if, not just 1. If we only had 1, then we wouldn't need the begin, as we talked about before. But if enable, we want our LED to be on. So LED would equal 1. Okay, and since we're in an always cone, right, I use the equal and not the arrow. And this is a mealy output. Again, when I use this double slash, that's just comments, right? As you know, that's not part of the code, that's comment. And then also, if the enable is a 1, not only do we turn the LED on, but our next state is gonna be state B. Right, so you see we put next state assigned to state B. Then we end. Okay, so this end goes with this begin. Okay, then we have an else. Right, so if enables not a 1, well, we're going to turn the LED off and we're just going to stay in state A. Okay, so you need a begin again here for the else. And then it's just LED 0. And next state would equal state A. Right, because we're just going to stay in state A if the enable isn't activated. And then we would need an end. We would need an end for this begin, and then we would need an end for the state. So we need another end here. See, this end is for the state A begin. Yeah, a common error, and it's one that I make a lot when I'm doing FSMs, is just making sure you're matching up ends and begins. It's very easy to miss an end or, have something that's not matching up. So that's a common error to look out for. And, when you get that error, I forget what the message is, but it's nothing like you're missing an end. You just get like a red line somewhere near the end, and you just got to kind of figure out, if you have enough by just matching them up. So I would just, be on the lookout for that. Okay, but do you see how what we wrote here for state A, do you see how that comes from the state diagram, right? Because this more output is just the output within the circle for state A. And then within the if, that's where your mealy output is going to be, right? Because your mealy output depends on not only the state, but also this enable input, which is an external input. Right? And then it also has where you're going to go next, right? If enable is 1, we go to state B, right? That's what the state diagram right here is telling us. If enable is not 1, well, then we just stay in state A, right? So that's what this is right here. So I think it's really important to be able to relate the code to the diagram, because if you can do that, again, this just becomes very cookbook, because now you're just going to repeat what we did for state A for all the other states. Okay, we'll do one more, and if you want me to do more, I'll do more, but I think if we do one more, I think that will be enough. So let's come up here, so not down below, and everybody can hopefully see. But now you would just do state B, right? So begin. Then we'll put count for state B, right? This more output, which is all zeros. So it's just going to be count equal to 3, tick mark B, all zeros. And with the semicolon, okay, then we're going to have our if. Right? And if enable, well, I look at my state diagram. When we're in state B, if enable is equal to 1, well, the LED is off, but we're going to state C. So here we would have, let's see, we need another begin here. Right, so LED would be off in this case, so 0. And then next state would be state C. Okay, and then we need an end. And an end to go with this begin. Okay, else begin. And now I'm looking at, okay, well, if enable is not active, I'm staying in state B and the LED is off. So LED equal to 0. Next state would just equal state B. And then I would need an end for this begin, and then another end for this begin here. Right? So this end is for the state B begin. Okay, so you get the idea. Do you think you could do state C and state D and state E? I mean, it's just following the same, right? You see how it's cookbook once you have the state diagram? And like we said, eventually, right after you have state C, state D, state E, you would need a default. Remember, defaults are important with case statements, because if you forget the default, then you're going to create a latch in one of these combinational blocks, which you don't want. That's added additional circuitry that you don't want that could possibly cause your FSM not to work. Okay, and I think what I did for my default is I just had next state going back to state A. So next state, state A. But you know, you could assign it whatever you want. And you know, you would need, like after this default, you would need like an end case, then an end module to finish it. Or actually end case, then an end for the COM block, the always COM, this begin, and then you'd have an end module. So yeah, it's really easy to mess up one of these ends, believe me. I think I always reverse these or something, but yeah, it's something to watch out for. Okay, so any questions up to this point? There's only two more things I want to show you. They're both on Canvas, so I got to pull down the screen and turn on the projector. I just want to show you in the activity, I want to show you what's different than these two lines and explain why I think this is better. And then also, I just want to point out something in the solution to the activity, something you've seen before, but I just want to remind you of it. But any questions before I pull down the screen and turn on the projector? Okay. Pick up the computer. Yeah, I know the resolution's not the best, but this is on Canvas. But here's the activity. So like I mentioned earlier, I went from state diagram to code. In the activity, you're starting with the code and then writing the state diagram. And what I wanted to point out here is that these three lines in the activity is a different way of declaring your states. Okay, this is more of a manual method, where what I showed you is more of an automatic method. And what I mean by that is, see here, we're explicitly typing in each state's binary number. Okay, like each state has to have a number that we express as binary. So, you know, if this was better resolution, what you would see here is this is parameter, then in square brackets, 2 to 0, meaning 3 bits, because each of our states has a 3-bit binary number because we have 5 states, right? And you can't represent 5 things with 2 bits, right? You need at least 3 bits. And then also your next state and present state are declared as logic. Okay, so that code I gave you, the software does this. The software will actually assign binary numbers to those state names that you give it under that enumeration. And you see the advantage, the big advantage, okay, especially when you take CPE133, because when you take CPE133, you're going to have a fairly large amount of code in your FSM. Now, the always FX is going to be short, but the always COM is going to be huge. Okay, it's going to be a lot of lines of code. And it's guaranteed that your FSM is not going to work the first time you try it. Okay, doesn't matter, you know, who does it, whether it's me, Dr. Hummel, you, anyone, you're going to have mistakes. It just happens. And if you do it this old way, if you have to add or delete things to, you know, as you're trying to get it to work, you know, edit, you're going to have to keep track of these binary numbers. You know, like if you go from 7 states to 14 states, well, now you need more bits to define those states, right? So you manually have to go in there and do that. But if you use the line of code that I gave you on the whiteboard, the software will do it. Like if you make any edits, the software takes care of numbering the states with binary numbers. So it's a big less of a headache if you use that enumeration type definition than trying to do it this way. Okay. So anyway, that's the reason for the difference. So, you know, as far as what you have to do for the activity, this doesn't even really matter. You know, it's this that determines what your state diagram looks like. Okay. And then one other thing I want to point out that's in the solution, that this is something that's asked if I don't, although it's something we did talk about earlier this quarter. And that's, if you look in the state diagram, now here's the legend for the state diagram. Notice that Z1 is inside the circle right here. So since it's inside the circle, what does Z1 represent? What goes right here in the legend? It's a more output. And then Z2 is up here. So what kind of output? That's the mealy. And then you have two external inputs. See, X1 and X2, those are external inputs. So like I said, even though my example just had one external input, you can have more than one, and this one has two. But the main thing I wanted to mention here, because like I said, if I don't mention it, people usually ask, although it's something we did talk about, and that's a dash. You see how sometimes an input is a dash in this state diagram? Do you remember in K-maps, we talked about a dash in a K-map or a truth table? What does a dash mean? Yeah, doesn't matter, right? It don't care. Same thing here. Okay, the dash in a state diagram just means that that input doesn't matter. That the transition from this state to this state will only X2 matters. And it only happens when X2 is zero, okay, not X2. Okay. So any questions about anything today? Because if not, you can go ahead, start working. The first thing to do is this activity. Just like before, each table passing one of the activities. And then after you do that, if you want to leave, that's fine. If you want to stay, that's fine. Remember, there's still quite a few people that haven't shown me the activity where you drag over an internal signal and then run the simulation. Actually, this section, I have more people than my other sections, but there's still about, it looks like there's still about 10 people or so. So if you haven't shown me that, do that by Thursday. Okay, you don't have to show me today, but you have to show me by the end of Thursday. And it can either be for lab 4 or lab 5 that you can show me how to do that. Remember, that's the Dr. Benson video, right? The troubleshoot video. She shows you how to do it there. You just have to show me that you know how to do it. And then after that, if you, well, has anyone finished lab 5? I mean, lab 5 is due this Friday. I wouldn't think anyone's done. Okay. Yeah, my other sections, I don't think anyone finished yet also, but that would be the next thing to work on is lab 5 because that's due Friday. Okay. All right. So if there's questions, please let me know. Blake will be here at 5.